Hi everybody, welcome to lecture 21 of Electrical Engineering 331. In this lecture we will talk about the Fourier series. Notice that we are now skipping over to chapter 5. Chapter 4 has applications of the Laplace transform. You will recall that in lecture 20 we talked about the applications of the Laplace transform a little bit, but there's more in lecture 20. And depending on how the timing goes for the course, we may come back to that topic later. But for right now, we're going to go to chapter 5 and talk about the Fourier series. In chapter 5, three different representations of the Fourier series are discussed. And we're going to talk about two of these in some detail. Today, in this lecture, we will talk about the cosine and sine representation. I strongly encourage you to go to page 206 of your textbook and look at table 5-3. There, it gives you a summary of all three representations. But again, as I said, today, in today's lecture, and also in the corresponding test, 21, we will only be dealing with the cosine-sine representation. So let's jump right in. What we're going to do in this lecture today is look at two different functions and find the cosine-sine Fourier series for the function. And we'll talk a little bit about how the Fourier series can help you to get more insight into a function. So anyway, the first function we will talk about is shown here, and this is problem 5.6 in your book. And I think everything here is pretty clear. So let's go ahead and go to your book, this table 5-3, and you'll see that the form for the cosine-sine Fourier series is given right here. A naught happens to be the average value of the function. And now, by the way, when we talk about the Fourier series of a function, we're talking about periodic functions. So we see the repetition here, and A naught is going to be the average value of the function over the period. So in other words, one way you could find the value of A naught, I mean, you can see here, this is the formula for A naught, and you can see that this is the average over the period. I guess I'll just say, if you can think of, in many cases, we'll be able to think of this integral as just an area under the curve, and you take that area and divide by the period, and you have A naught. But the formulas for AN and BN are a bit more complicated, and they're given here. Now, we're taking T naught to be the fundamental period of this periodic signal for which we want to find the Fourier transform. And so this omega naught that's coming in here and also down here, that is 2 pi over T naught. So once you find T naught, you immediately can get omega naught. And that's about all that we can say before we jump into this, except that let me just, in terms of motivation, say that, again, the Fourier series, I mean, at this point you might be wondering, well, why do we want to calculate this? Well, we're going to find out soon that expressing functions in terms of sinusoids, as we are doing right here, can be very useful. it's particularly easy to find the response of a circuit from any circuits is particularly easy to find the response of the circuit to a sinusoid. And so if we can decompose a signal into sinusoids, then we can find the response of the circuit to that original signal. So that's one thing that's nice. But another thing is that, as I mentioned a few minutes ago, the Fourier series can help you to have insight into a function, and we will particularly see that with our second example in this lecture. So anyway, let's go ahead and proceed. So the first thing we're going to observe about this function is that t0, the fundamental period, is equal to 4. And you can see that because if you take any value here, let's say -1, now admittedly the function will have that value again just 2 time steps later at +1. But that doesn't mean that 2 is the period here, because let's think about a counter example. Okay, to see that the period is certainly not 2, we can see that at t equals 0, the value of the function is 0. 2 time steps later, the value of the function is 10. So even though if you compare -1 and 1, which are 2 time steps apart, then indeed this function has the same value. But in general, this function does not have the same value. If the value at, when you compare the value at f of t and f of t plus 2, it does not in general have the same value. But if you compare f of t and f of t plus 4, it does. For instance, at -1 and at 3, it has the same value. At 0 and at 4, it has the same value. At -2 and 2. So the period for this function is 4. So t0 is equal to 4, and then omega naught is 2 pi over t0, so that's 2 pi over 4, or pi over 2. Now, the next thing that we observe is sort of interesting, so I want to talk about it in a little more detail. This next observation says that f of t is an even function. And what that means is that f of -t, for any t, f of -t is equal to f of t. Or in other words, another way of saying it is that it has symmetry about the vertical axis here in the middle. And we can see that, but that has an important implication. One way to look at this is the following. The cosine terms here in the Fourier series are all even functions of t, and the sine functions are all odd functions of t. And the fact that this function is a perfectly even function means that it has no odd components. So therefore, all of the bn's will go to 0. Now, you may not be satisfied with that kind of an explanation, and so let's come down here and see if we can understand why it's true. Now, one thing that's important to realize is that for all of these 3 formulas here, the limits are 0 to t0, but we don't have to use those limits. We can integrate over any period of the function. So if it's convenient to integrate from 0 to t0, then do it. But if it's more convenient to integrate from -t0 over 2 to +t0 over 2, well, then do that. And so let's think of this integral down here, the integral for bn. Instead of using 0 and t0, let's think of the integral as being from -t0 over 2 to t0 over 2. Again, that doesn't change anything. Okay, so we have the integral from, t0 over 2 to the left of 0 to t0 over 2 to the right of 0. Now, we've already said that f of t is an even function, and sine of n omega naught t is an odd function. Now, an even function multiplied by an odd function will always be odd. So this is overall, this argument here is an odd function. And when you integrate any odd function over what's called symmetric limits, in other words, from negative t0 over 2 to t0 over 2, whenever you integrate an odd function over symmetric limits, you get 0. So that's another way of seeing that Bn is equal to 0 for all n. And the final thing we can observe is that we can find a0 very easily, because remember, it's just this integral of f of t over 1 period divided by the period. Well, if we integrate this function, it's just the area under the curve, which, since this is a triangle, is real easy. So we have here the average value of f of t over 1 period is, okay, the area of a triangle is 1/2 base times height, so that's 1/2. The base is 4, the height is 10, and then t0 was 4, so we have 1/2 times 4 times 10, or 20 over 4, which is 5. So a0, the average value of this function, is 5. Okay? So if we now substitute in everything we have found out a0 is equal to 5, we have found that all the bn's are equal to 0, and we have found out that omega naught is pi over 2, and so this formula for the Fourier series of f of t becomes this formula down here. Okay, and so now we want to find these ANs. We have found out everything that we need in order to complete this problem except for the ANs. So let's go ahead and finish this. Now, AN, the formula for AN is given here. Okay, let's think. We have 2 over t0. Remember, t0 is equal to 4, so 2 over t0 becomes 2 over 4, or 1/2. And we get 1/2 the integral. And again, as I said a moment ago, it's okay if we integrate from negative t0 over 2 to t0 over 2 if that's more convenient. And it is going to be more convenient in this case, and I'll show you why in just a moment. So, but now again, I want to stress, if you would prefer to integrate from 0 to 4, you will get the same answer, but I'll show you why I would prefer to do it this way in just a moment. So, okay, so I'll integrate negative 2 to 2 f of t cosine of n pi t over 2 dt. Now, here I'm pulling some kind of a trick, and let's see what this trick is. Okay, f of t is an even function, as we have already observed, and cosine is an even function. Now, just like up here when we said an even function times an odd function is always odd, well, an even function times an even function is always even. And when you integrate an even function over symmetric limits, what you can say is that that's equal to twice the value of the integral of that same function over just half, the right half of that region. So notice that I've changed the lower limit from negative 2 to 0, and I've put an extra 2 out here in front. Now again, you don't have to do this. In fact, as I'm going to show you in just a moment, I suggest that all of these integrals that we will be doing when we do the Fourier series, I suggest that for all of them, you use Wolfram alpha. So what that means is that you don't have to worry about little tricks like this. You can just use Wolfram alpha directly. But I think it's nice to be aware of things like this, because it saves you some writing. I mean, let's think about what would happen if you didn't do what I did here. If you had integrated just straight from 0 to 4, you would have had to have typed in more, because from 0 to 2, the value of this function, see, I'll say it this way. From 0 to 2, this function has one expression, and from 2 to 4, it has another expression. So you would have had to have broken up your integral into two parts if you integrated from 0 to 4, you would have had to have broken up your integral into two parts. And so it's not a big deal, but you do have to type in twice as much stuff into Wolfram Alpha, and then do arguably twice as much simplification as well in order to get your final answer. But what I did instead was I integrated from -2 to 2, and now if I left it at that, I would still have two different integrals. But then, using that trick that this is an even function over symmetric limits, I said, well, I can really just integrate from 0 to 2 and double it. And so that saved me a little bit of typing, that's all. But if you don't like those kinds of simplifications, don't worry about it. Just go ahead and plug in what you have, and in fact, we'll see in our second example that well, to be honest, in our second example, there is a trick you could pull, but you'd have to be very, very alert to see that trick. And so we won't approach that one with any tricks at all. We'll just plow through it doing the brute force method, and you'll see how it goes. Okay, so anyway, so we have this expression for f of t, and as we argued here, we can get by with just integrating from 0 to 2, and now finally, okay, the 1/2 times 2 gives us 1 out front, but finally now we have to figure out what f of t is in this region from 0 to 2, and that's really pretty easy. From 0 to 2, notice that at t equals 0, f is equal to 0, and at t equals 2, f is equal to 10, and it's linear, so that just tells us that f of t is 5t. So that's what we stick in down here. And so finally now, we have a nice, neat expression for an. And so now I'm going to pause the video for just a moment so that I can type this in and to Wolfram Alpha, and then I'm going to resume the video so that you can see exactly how it looks in Wolfram Alpha, and then we will proceed from there. So let me pause for just a moment. Okay, so once again, what we have here is an is equal to the integral of 5t cosine of n pi t over 2 from 0 to 2. And I think you'll be impressed with just how simple this is in Wolfram Alpha. So we go to wolframalpha.com, and you just type it in just like I said it. Integral of 5t cosine. Now notice I did not put an asterisk there between the 5 and the t, between the t and the cosine. I could have, but it wasn't necessary in that case. Now, on the other hand, inside the argument here, if I had run all these letters together, the n and the pi and the t, and had just written it as npit, it wouldn't have known what that meant. So if in doubt, just put the asterisks in. So in other words, like I say, if in doubt, just go ahead and put your asterisks in here, and you can also put in one there as well. 5 times t times cosine of n times pi times t over 2. And notice how we just write this out in straight English from 0 to 2. It's really remarkable the way this works. It's just so convenient. And so then you hit return, and you can see it takes just a moment, and you have your answer. Now, this answer is 20 pi, excuse me, is 20 times parentheses pi n sine pi n plus cosine pi n minus 1 over pi squared n squared. So let's come back here to OneNote, and you can see that I've written that same thing down here, 20 times parentheses pi n sine n pi plus cosine n pi minus 1 over n squared pi squared. Now, we can actually simplify this a little bit more because, see, Wolfram Alpha has computed this assuming n could be any real number. But for our purposes in this problem, n is an integer. I mean, n is the index. Where is n coming from? It's the index on this sum, and that is understood to be an integer. So we only have values n equals 1, 2, 3, 4. It's just the counting numbers. And so in view of that, we know that sine of n pi is equal to 0. So this first term goes away. And likewise, we know that cosine of n pi is the same thing as negative 1 to the n. Now that may not be obvious to you at first, but think about it. When n is equal to 0, you have cosine of 0, which is 1. When n is equal to 1, we have cosine of pi, which is negative 1. When n is equal to 2, we have cosine of 2 pi, which is 1. And when n is equal to 3, we have cosine of 3 pi, which is negative 1. So whenever n is even, we get 1. Whenever n is odd, we get negative 1. And a way to summarize that write that very compactly is just to say negative 1 to the n, because this expression as well is equal to 1 whenever n is even and negative 1 whenever n is odd. And so this expression here for a sub n can be written more compactly like this. And again, remember, bn is equal to 0. So when we substitute in what we have found for an into this formula, we get this. And that is the Fourier series of f of t. And as far as insight into this is concerned, one thing we can say is that this is a completely even function of t, and that's pretty obvious because, of course, the constant is an even function of t, and all of these terms are even, so that pops out immediately. And another thing that we see is that these coefficients are decreasing fairly rapidly. They are decreasing with n squared. So as n gets bigger and bigger, these terms will pretty rapidly, these coefficients will pretty rapidly get smaller. And so therefore, we would expect that it wouldn't take us too many terms here in this expansion to recover this function up here. So that is our first example of the Fourier series. Now, for a second example, we are going to look at problem 511. Again, we want to find the cosine sine Fourier series representation of f, but now f is considerably more complicated. So we want to be careful to do this very precisely, and so let's see what happens. Well, the first thing we can see is that when we ask ourselves, what is t naught? I mean, this certainly is a periodic function. We can see how it's repeating, but what is t naught? And if you look at this part here, starting at negative 4, it doesn't repeat again until we come over here to 2. So that tells you that the period is 6. Now, if the period is 6, since omega naught is equal to 2 pi over the period, omega naught will be pi over 3. Now, this function, if you just look at this function, it is neither even nor odd. So that means that in general, we're going to need both ANs and BNs for this function. Although something very interesting is going to happen at the end, but we'll hold off and see that in just a moment. Now, what about the average value of f of t? Well, we are going to be able, fortunately, to find that pretty easily. Remember that a naught is 1/6 times the integral of f of t over one period. And so if we think about the integral of f over this period, it's just the area of this triangle plus the area of this rectangle. So we have 1/6 times 1/2 bh, that's the area of the triangle, plus 2 times 100. Why that? Well, because the width is 2 and the height is 100. And here then 1/2 b is 2 and the height is 100. So we have 1/2 times 2 times 100 plus 200, which is this, again, remember, is the area of the rectangle. And so we get altogether 1/6 of 300, which of course is 50. So the average value of this function over a period is 50. Okay, now our formulas for AN and BN, when we plug into the formulas we saw at the beginning of the lecture, the formulas that are on in table 5-3, we get 2/6 because it's 2 over t naught times the integral from 0 to t naught of f of t cosine of n pi t over 2. This is omega naught t, n pi t over 3. I think I said 2, but it should be cosine of n pi t over 3 because, again, remember that omega naught is pi over 3, so this is in omega naught t. And similarly, same thing over here, except we have sine instead of cosine when we're talking about the BNs. Okay, so again, as I said earlier, here I'm not going to try to pull any tricks and to write this in any kind of shorter form. We're just going to go ahead and plow through this, sort of the brute force method. So let's do AN and then we'll do BN. So for AN, okay, 2/6 is equal to 1/3. Now we're integrating f of t cosine of n pi t from 0 to 6. So let's see what we get. Okay. Well, from 0 to 2, f of t is equal to 0. So we don't have to integrate there. Our integration then will start at 2, and from 2 to 4 we have one expression. And then from 4 to 6, we will have another expression. Okay, so let's see how this will go. What is, see that, now we have to, the cosine of n pi t over 3, we can see that in each integral. But what about the f of t? What's the expression for f of t from 2 to 4, and what's the expression for f of t from 4 to 6? Well, from 4 to 6 is easy. F of t is equal to 100 between 4 and 6. So that's why we have 100 right here. But what is f of t equal to between 2 and 4? Well, you can see that f declines by 100 in 2 horizontal steps. So the slope is -50. So between 2 and 4, that means that f of t is equal to something minus 50t. Because again, the slope here, it goes down 100 units in a horizontal distance of 2 units, so the slope is minus 50. So it's something minus 50t, and if you look for a moment, what that something is 200. 200 minus 50t, and you can easily check that because 200 minus 50 times 2 would be 200 minus 100 and give you 100, so it checks there. And 200 minus 50 times 4 would be 200 minus 200, which is 0, and it checks there. So 200 minus 50t is a linear function with a slope of -50, and it agrees at the 2 endpoints with this line, so it must agree everywhere. Because, as you know, 2 points determine a line. So that takes care of f of t in the region between 2 and 4, and between 4 and 6, f of t is just equal to 100. So this is our complete expression for AN. And of course, for BN, once we have AN written down, it's easy to get BN because we just have exactly the same expression, but everywhere we have a cosine up here for AN, we will substitute sine for BN. Now, I would strongly suggest that you use Wolfram alpha. Now, I'll be honest with you, I did not try in Wolfram alpha, I did not try doing both integrals for AN at one time. It may have worked, I'm not sure, you can try it, but I did each integral one at a time. And then whatever I obtained, I multiplied it by 1/3. So for AN, this is what I obtained. All of this. this whole stuff here. And again, I obtained that by plugging in this to Wolfram alpha, and then plugging in this to Wolfram alpha, and then multiplying both of those by 1/3. So this is what I got, this whole stuff. And when I repeated that same process, but putting in sine instead of cosine everywhere, then this is what I got for Bn. And so let's see if we can simplify these things a little bit. Now, pay close attention because it does simplify, so I want to show you how this goes. So f of t, remember, a0 was equal to 50. So f of t is equal to 50 plus the sum n equals 1 to infinity of an cosine omega naught t plus bn sine omega naught t, where omega naught, I should say cosine n omega naught t plus bn sine of n omega naught t, where omega naught is pi over 3. Okay, but what are the an and bn? Well, we have just derived these formulas for an and bn, but they can be simplified a bit. So let's see how this will go. Okay, if we look at an, we can see that first of all, this term, and again, remember that we have not told Wolfram alpha that n must be a counting number. So that's why Wolfram alpha has included this term here, 3 sine of n pi. But since we know that n is equal to an integer, that will go away. Okay? And then the minus sign, I'll pull that out front. Now the pi n, remember, if this term is gone, then pi n here, this pi n can cancel with the pi and n down here, and so that's why I have, instead of n squared pi squared down here, I have pi n. And then the final thing to observe is that, okay, we have 100 out here, plus we have that negative sign, so that's negative 100. And you can see the sine of n pi 3 times 2. Now remember, we've already taken care of the negative sign, and the pi n has already canceled down here. So what we're left with is sine of n pi 3 times 2 times cosine of n pi 3, which is the same thing as 2 sine of n pi 3 cosine of n pi 3. And you might remember 2 sine x cosine x is the same thing as sine 2x. So this sine of n pi 3 times 2 times cosine of n pi 3 just becomes sine of 2 pi n over 3. So this term right here, sine of 2 pi n over 3 times 100 times minus 100 over pi n, that takes care of this first term up here for an. And then what about this second term? Well, again, the sine of 2 pi n goes away, and so we're left with minus 100 sine of 4 pi n over 3 over pi n. So that can be grouped in immediately. It has that minus 100 over pi n term already, just like this does, and so we can then just slip in the sine of 4 pi n over 3 right here. So this is what an is equal to, and remarkably, that is actually always equal to 0. Just try it for n equals 1 and 2 and 3 and so on, and you will see that every single time it's going to be equal to 0. So that's pretty remarkable there, because remember that the an's are the coefficients of the cosine terms. Right here. Here's the easiest way to see it. The an's are the coefficients of the cosine terms, which are the even terms. So the only even term in this function is 50. Everything else in this function is odd. And that is something that we could not, I don't think anybody could have easily seen that by looking right up here. But essentially what that is saying is that if we took this function and everywhere we subtracted 50 from it, we would get an odd function. And you see, that's the kind of insight that the Fourier series will bring to you. I think it would be very hard to see that otherwise, but once you look at the Fourier series, there it just pops out. Well, anyway, we'll get back to that point in just a moment, but to finish this problem, so the formula for Bn is given right here, and so let's see about the simplification of that. This one does not simplify nearly as much as the formula for An did. In fact, if you look at this, the only thing that looks like it will simplify is right here. Again, since n is an integer, the cosine of 2 pi n is always going to be equal to 1. And so that's why we have a 1 down here. But otherwise, there's no simplification in the expression for Bn. And so that is it. Here is our expression for f of t, right here, where all the an's are 0, so we wouldn't have to have that. That could drop out, and the bn's are given by this somewhat lengthy formula right here. And the last thing I'd like to show you is what happens if you actually take our original function f of t right up here, and I want to emphasize again, let me make sure you understand why I'm saying this, what the importance is here. So let me go over it one more time. All of these an's are equal to 0. So all of these cosine terms drop out. And f of t is just equal to 50 plus the summation of a lot of sine terms. All of those sine terms, each of those sine terms is odd. So this whole expression right here, this summation is going to be an odd function of t. The only thing that messes f of t up from being odd is this 50, because 50 is even. So if we take f of t minus 50, if we just take 50 away from f of t, we will be left with a purely odd function. That's what this analysis is telling us. And so let's plot f of t minus 50 and see, is this really an odd function? Well, remember that what an odd function, what that means is f of negative t equals negative f of t. Well, let's try a few t's and see if it's true. If we try f of negative 1, we get 50. If we try f of positive 1, we get negative 50. Okay, it works out there. What about at 2? F of 2 is 50. F of negative 2, negative 50. Okay, it works out there. What about f of 2.5? F of 2.5 is 25. F of negative 2.5 is negative 25. F of 3 is 0. F of negative 3 is 0. And of course, 0 is the negative of 0, so that's fine. What about f of 3.5? F of 3.5 looks like it's negative 25. F of negative 3.5 is positive 25. And so on. You will see that indeed this function really is an odd function. So to me, that's just really remarkable. Again, I think that if you look at this original function, it would be very hard to see that you could subtract 50 from that function everywhere and obtain a purely odd function. But Fourier series analysis has helped you to see that. So that's the last example. Once again, I strongly encourage you to use Wolfram Alpha or some other, if you have some other symbolic algebra manipulator, like for instance, Maple would do this, and I believe Mathematica would also do this. And so if you have access to those, that's great. Or who knows, maybe even some of you have a calculator that will do symbolic algebra, and that would be great too. But we could do these by hand. We can do these integrals. They're not that hard. For instance, just think about this integral right here. You can see that we can do this integral by integration by parts. But I don't think that that's a whole lot of fun. So I strongly encourage you to use Wolfram Alpha. So anyway, that's the end of lecture 21, and good luck.